Hi everyone. In this video I'm going to talk you through a tutorial for doing some basic statistical analysis in the R statistical software. Now technically this video is part of a workshop, but if you just happen to have stumbled across it, the tutorial is actually on our GitHub page and we have a link to this page in this video description. So the goal of this video is not to teach you how to do statistics. We'll assume that you have some basic understanding of this, but perhaps you've learned this in SPSS or in Stata, and now you want to learn how to do this in R. And that's where we've got your back. So we're going to focus on the basic t-test for comparing the means of two groups. We're going to do some basic ANOVA for comparing the means of multiple groups, and then some basic ordinary linear regression analysis. So for this tutorial, we'll be using some data from Thomas Piketty from the Capital in the 21st Century book. And you can find the files via this link, but we've also got an already pre-processed version on our GitHub page. So you can just run this piece of code to download the data and make a nice tibble out of it to use with the tidyverse. And it looks like this. So here we see that we have some data where for several years and for several countries, we have some data on the public and private capital accumulation. And this is what we're going to use for our analysis. And it's not some, of course the data is interesting, but for now we're mainly just interested in having some continuous data and some nominal variables so that we can show you how you can use these different statistical techniques. So to start off, let's go look at some basic t-tests, which you can use to compare two groups in our data, so the means of two groups. And to do this, we're first going to divide our data, or basically add a grouping variable to our data, where instead of looking at individual countries, we're just going to say we're going to look at Anglo-Saxon versus European countries. And the way we're going to do this is we're going to say, well, these are the Anglo-Saxon countries in our data, and in all the countries in our data which are not Anglo-Saxon, we're going to name these are part of the European group. So this here is of course code from the tidyverse. If you need a refresher there, we have some tidyverse tutorials on the GitHub page as well. But here we basically just say, if the country is one of these Anglo-Saxon countries, give it the value Anglo, and otherwise give it the value European. So then we see that we now have 164 rows of Anglo-Saxon countries and 205 rows in our data for European countries. Or to be more specific, we see that we now have this additional variable here, which just tells us, well, this is an Anglo-Saxon country and this is a European country. So now we can do a t-test using these groups. And we're going to start with just an independent samples t-test. And in a minute, we're going to tell you why this is actually wrong to use in this case. But we're just going to demonstrate it to show you how to do this type of test in R. So an independent sample t-test, as you know, just looks at two groups and then takes the mean value for these two groups and compares them. So in this case, we're going to use t-test with as a dependent variable the private capital, as an independent variable this Anglo versus European groups. And then what it does, it just takes this column, it takes the mean values here for the Anglo-Saxon countries and the mean values for the European countries, and then it compares those. Now, if you see how this t-test function works, the first thing that jumps out is that we have this weird tilde symbol here, and that might actually be new to you because you don't see this very often in R functions. Often you just have some named arguments. But in this case, when you're working with statistical functions, you will often see this formula notation. This tilde betrays, it tells you basically that we're looking at the formula. And this formula is quite standardized in statistical functions in R. It's often the case that things before this tilde, this wavy symbol here, is the dependent variable, in this case the private capital accumulation. And after the tilde, we list our independent variable. So in this case, our two groups, Anglo-Saxon versus European. Now if you want this, we already do the t-test, and then you basically see the results that you would expect here, right? So you perform the t-test, it tells you, well, the mean value for private capital accumulation for the Anglo-Saxon group was 3.75. For the European group, it was 4.30-ish. And then here we have the results of the t-test, which tells us whether the difference here was actually statistically significant. And here we see that the p-value is lower than 0.001. Notice, by the way, that the p-value here is noted in scientific notation. So here this e minus 0.06 indicates that this number is not 4.69, which would of course be an impossible value for a p-value, but is in fact much lower. If you have trouble interpreting scientific notation, what you can do is force R to print it with more decimals. So here it cuts off the decimals and then goes on to scientific notation. We can also say things like, let's see, printf. And this tells us I want to use, for instance, 9 decimals. Then you see that the value is indeed much lower than 0.001, which is one of these typical thresholds we use in statistical testing, meaning in this case with 99.9%, we're going to assume that there's a statistical difference between this mean of 4.29 and this mean of 3.74. Now, as I already alluded to, it's actually incorrect to use an independent samples t-test in this case, or, well, at least not appropriate. So next we're going to do a paired samples t-test. But let's first look a second at why this is actually problematic. So if we look at our data, we see that while we do have these observations of private capital within our groups, these are actually nested in years. So we have observations from 1970, 1971, 1980, etc. And as we look at them, we actually see that these values are not at all independent. For both the Anglo-Saxon and European groups, we see that the private capital clearly goes up over time. So instead, it might make more sense to do a paired samples t-test. Let's first do a short visualization to show you actually how what our data looks like. So we're just going to do some basic aggregation. Again, if you need a refresher in Tidyverse, please look at the tutorials. Here I'll just say that we have our capital data. We're going to drop our missing values. So here, for instance, for Spain, we see that we have some NAs. We're going to drop them. Then we're going to aggregate the data, for which we're going to group by year and group, in this case group being Anglo versus European. And then for those groups we're going to take the mean of the private value, the private capital. So here we're going to group all these countries together within groups per year. So now our data looks like this. And now we can plot this data, Ggplot. Which gives us this plot here. So we're looking at the private capital over time from 1970 till 2010, separately for the Anglo-Saxon group and the European group, and to see that in both cases this value goes up. So here you clearly see that it doesn't really make sense to just act as if these observations were independent. Instead, it might make more sense to per year see what the differences between these values were. So this is something that we could do with a paired samples t-test. And before we do a paired samples t-test, we actually need to reshape our data a bit. Because as you might know, if we have data like this, then an independent samples t-test makes sense because we're saying, well, this is for instance a dependent variable, and then this is our independent variable. If we're doing a paired samples t-test, we need to make sure that within every case we have two observations that we're going to compare because they need to be paired. And as the way the paired samples t-test function works in R, we actually need to make sure that these are two different columns in our data frame. So we're going to pivot the data to a wider format, which again is described in the Tidyverse tutorials. And then our data looks like this. So now instead of having the data stacked like this, we have longer data where we have the Anglo and European data in separate columns. And now we can do a paired samples t-test where we're going to compare this value to this value and then basically look at the difference, the mean difference. This simply again uses the t-test function, but this time we're going to apply it slightly differently. Now we're actually going to say, well, we have these two values. There's two different columns in our data, two different factors, if you will. and we're going to tell them that they're paired. This also means, of course, that these factors need to be of the same length in order to compare them, which is the case because there are columns in the same data frame. And then the interpretation is more or less the same. And instead of giving us the mean for both groups, it just gives us the difference, the mean of the difference between these both groups. And then the interpretation of the statistical part is of course the same. And again, we see that there's a p-value, which if we take into account this scientific notation, is much lower than 0.001. So indeed, there's a significant difference between these two groups, which is also what you would expect if you just look at this plot. So this is really all there is to say about how to do t-tests. With this you should be fine. But of course, if you want to report this stuff, you'll typically also report the mean and standard deviation. Well, there's not a lot of magic going on here. By now you probably know how to do some basic aggregation stuff in R. But in this case, if we just have these values, we can simply call the mean function. So from the per group Anglo column, we just want to take the mean value and the standard deviation value. We want to do the same for the European group. And then basically we have all the data that we need to, well, basically report a t-test in a nice kind of format, in a nice kind of way. So for instance, in the APA format, the typical thing to do would to basically say, well, we have this variable which has this mean and this standard deviation. We have compared it to this one with this mean and this standard deviation. And we can tell you that the t-value with 40 degrees of freedom is minus 0.6533, which corresponds to a p-value being lower than 0.001, so meaning that this difference is indeed statistically significant. So now let's move on with Anova. Let's first clean this up a bit. Well, not remove our data, of course, we'll still need it. So Anova is basically what you would need if you want to do a t-test, but you have more groups than two. So in this case, we're not going to just compare Anglo-Saxon versus European, but maybe we actually do want to compare all the individual countries, which means that we have more than two groups. The first thing that we're going to need to do is we're going to need to tell R that our data that we have here for our country is actually a factor. And just as a quick refresher there, in R you can have columns which are character vectors. In this case, it just thinks of these piece of text as characters. But we need to make clear to R that these values are actually labels, which basically means that the values are occur multiple times. And then it makes more sense to think of them as that you have a specific group, Australia, which occurs multiple times in your data. And that's important because this tells R that we can now treat them as basically nominal variables. A nice thing to know about the plot function, which you probably know, that it is very versatile. So in this case, if you just use the plot function and you also plug in this formula notation, where you say, well, I'm going to look at private as a dependent variable with capital country as an independent variable, that's actually a way to create a box plot. By the way, if you see a box plot like this and you don't see all the variables, all the names on the x-axis, it just means that your plotting device is not wide enough. For a general thing to think about when you're working with R is that how things are plotted depends on how big your plotting screen is. So you sometimes might want to shift this around a bit. Oh, I actually can't properly fit it onto my page here because everything needs to be big enough in order to record it. Now you do see that it works like this. So what we see in this data, let me just show it like this again. What we see in this data is that we have for different countries, so these different private capital scores, and based on this box plot, we can already see that there are some differences here. So here you have some countries which are quite similar, but then here there are some countries with much larger values. Also, by the way, we see that we have Japan here, which actually isn't technically an Anglo-Saxon or European country, but perhaps we should have removed this from our data, but bear with us now, just consider it a group. So we're going to compare these different countries. And what we're going to do is we're going to run the Anova test, which just simply tells us whether these groups overall, there is a statistical difference in their means. Running the Anova is actually really simple in R, but there's an important thing to take into account here. There actually is a function in R which is called Anova, but that's not the function that you're going to use when you do an Anova analysis of this statistical sort. We're actually going to use this later on when we're comparing different linear models. Now for now, what we're going to use is the AOV function for analysis of variance. That's the function that you need for the statistical Anova test. So how this works here is, again, we're using this formula notation. We're saying, well, here before the tilde we have the dependent variable, which is again our private capital accumulation score, and we have as the independent variable we have this group of countries which needs to be a factor, and in this case can have 2 or more groups as opposed to the t-test. Also note that instead of just running this code and getting the output, we've actually assigned the output to m. There's a good reason for this. It just means that now m refers to the output of analysis of variance test, and for some types of statistical tests, it's you need special functions to properly look at them. And also has some additional benefits. You can save models like that. You can sometimes do special visualizations with them. So typically this is often how you want to run a statistical model. You want to assign the output to a name and then work with that name to interpret it. So here just summary of m just gives us the summary of the results of this Anova test, which here just tells us that the test is indeed significant. And as you probably know from Anova, this is basically all it tells us. It just tells us if there was a statistical difference between the means of these groups. But it doesn't yet tell us which of these groups were actually statistically different. So based on this plot, we might make a guess that France has a lower private capital score than Spain, for instance. But typically you would also want to show this, right? So then so how we often call this is the idea of doing a post-hoc test, where you can do a pairwise comparison. So basically, again, a statistical analysis of 2 groups, but for all the combinations of groups. And what we're actually using here in this case is the pairwise t-test. And with the Bonferroni adjustment, which is also the one which you often see when you do this in SPSS, I think. But in any case, if you see how this function is called, it tells us, well, here it doesn't use the formula notation actually. We just say first this is the dependent variable, this is the independent variable. And then what we get is a matrix with all the p-values for the combination. So telling us that there was no statistical difference between France and Australia, but there was a statistical difference between France and Spain, and France and Japan, and France and Italy, which is also what you would expect if you were looking at this box plot. So that really in a nutshell is how to do Anova analysis in R. So then as a final step, of course, whenever you're reporting these Anova results, you would like to report the means and standard deviations of the groups as well. So we did include some bit of code to how to do this in the tidyverse, but we really don't need to discuss it here because it's not that hard. And then we can move on to linear models, or otherwise the ordinary linear regression analysis that you all know and love. And how we're going to do that in R is we're going to use the LM function, which just stands for linear model. Well, let me first clean up my R session a little bit. Right, that's better. So let's first look at what this formula looks like. So again, what this code looks like. And again, the code, the function has a formula input here. And the formula input is similar as the one we saw before. So we have the tilde, and before the tilde there's the dependent variable, and after the tilde there's the independent variable. But in this case it's actually 2 independent variables. So country plus public. So we're going to do a multiple regression here. And if you know your regression analysis, you actually see that this dovetails nicely with how you specify a formula for regression. So you have a dependent variable predicted by some linear combination of these independent variables. Now, Another new thing that you might be seeing here is this data is capital, which means that we're going to specify what data we're using in this linear model. And then here we're saying that we're going to use the capital data frame. And what this means is that by including the data here via this argument, we no longer need to specify where these vectors come from. So for comparison, if you look at the t-test that we did before, you saw that we did capital $ private, meaning that we want to get the private column from the capital data frame. Now this is easy if you just have 2 variables to include, but then in a regression model you might have like 10 independent variables, and then it just becomes tedious if you have to repeat this capital $ thing everywhere. So instead it's then often more nice to just say the data is the capital data frame, and then we can directly refer to the columns from this data frame in our formula. So now let's actually fit the model. And again, we're assigning it to a name and then separately investigating that variable, which as you'll see in a minute also allows us to plot some model diagnostics. Now the output of a regression model, if you look at it here, it's a bit convoluted. In a minute, we'll also show you a nicer way to visualize these regression tables. But for now, just bear with the raw output as R gives it to you. So actually, this is just a table with all the fixed effects. So here we see the independent variables of our model. Notice that here we have the intercept. And then for the intercept, we of course know what the intercept was. You have the standard error, t-value, and the p-value, whether it was significant and not. Then here we have the independent variables for the country variable that we included here. And notice that we actually have now automatically split this up into a whole range of country level dummy variables. And this is because country is a categorical variable, a nominal variable. And how we specified it in R is as a factor. So since we give it as a factor, R automatically says, well, then probably you just want to split this up into different dummy variables, right? Also notice then that if you do this, you of course need some kind of a reference category. So in our country data, we see that our first level is Australia. And this is also why if we then look at the model output, we actually don't have an effect for Australia, because Australia is technically the intercept here. And then all the other countries, we see how much it differs from Australia. This actually sometimes isn't that convenient that we need this kind of reference category. I mean, sometimes it makes sense, but sometimes not so much. And a nice thing to know about R is that you can also ignore the reference category. If you say -1 here, it just says, well, let's actually fit the model without an intercept. And then instead of the intercept, we're just going to use all these dummies. So here, now you do have Australia included, and all the estimates are their own intercepts. So now we have multiple intercepts in a sense, as opposed to one intercept and the differences from them. If you're not familiar with this, you need to be careful with it because it does change some things, such as the R squared value, which is now super huge, which is different from what it was before. So don't just use this if you don't know what you're doing, but just beware that it's something which you can quite easily do in R, and it's actually quite convenient for some types of analysis. Now let's move on with our examples. So here, the next one is actually what I just did. So it's also described here a bit in how this works with the -1 and ignoring the intercept. Now let's move to this example here, where we're going to discuss how, first of all, instead of country, we're going to use the group, which makes for a slightly less complicated regression analysis because then we don't have all these countries included. But in here, what we're going to say is we want to have an interaction effect of group and public. Oh, by the way, before we move on, we should say that this isn't very appropriately done because our data, of course, still includes time. So just ignoring that time aspect of it isn't proper for a regression analysis. Normally we do some more complicated time series or aggregate data first. But again, this is mainly just to show you how to use these models and not how to use them properly. So with that disclaimer, we're now going to fit these two models. So here first we're going to fit a model where we say private is a dependent variable and group and public are the independent variables. Just to show you that's this model. So you have an intercept. We have group European. So in this case, it's European compared to the reference category, which is the Anglo-Saxon countries. So here the reference category is quite doable, right? If you only have two variables, then it's this actually makes a lot of sense. And now here we have the public as an independent variable. And now we want to see whether there's actually an interaction effect of this public as predicting the private capital for whether the group is European or Anglo-Saxon. That's what we do here. We say, well, have group as an independent variable, public as an independent variable, and then a name double dot other name means includes the interaction effect for this combination. Now, you see that we actually have assigned it to M1 and M2 here, and there's a good reason for this. Typically, when you report these regression tables, or even if you're just interpreting them for yourself, it makes a lot of sense to put them side by side. And this is also often what you'll see in scientific papers, right? You'd have one table, you should have different regression models side by side, so you can see what happens if you add certain variables, so you change some stuff. So that's also what we're going to do here. And for this, we're going to use the Ggplot package, which I think stands for strenge Ggplot, which is something German. You don't need to know the German word, but it's actually a very useful package. There are actually several packages in R which can help you nicely visualize regression results. Strenge Ggplot is one of them. TextReg makes a bit more sense if you want to prepare your data for working with LaTeX. Stargazer is another alternative. But the Strenge Ggplot package I particularly like because it also does some cool other stuff with analysis. And you'll mainly see that when we move to the advanced modeling parts, because then you see how it also includes some additional measures such as pseudo-error measures and stuff. It's a quite powerful package for analyzing statistical results. So here in the Ggplot package, there's the tab model function, make a table for a certain model. And here we can just plug in multiple models. And if these models are just all regression models, it will automatically just plot them side by side in this really nice classic type regression table. So here you see both models on the left and right, and then here you see the independent variables. So you see, for instance, that in the second model we also have the interaction effect, and we see that the interaction effect is negative and significant. Also notice that here you have some nice information such as the confidence interval, and of course you can tweak this a bit. So you can say, well, I want to include standard errors and no confidence intervals or something else, often just depending on whatever any scientific journal would want you to report. So this is actually a really nice way of making regression tables because they're already directly usable in your papers. Actually, a pretty cool thing about this is that these tables themselves are in HTML format. So if you press this button and you export them, you just open them in the browser, you can just directly copy paste them into a Word file, and it's quite nicely formatted immediately. So it's quite easy to include these regression tables in your papers. And that's stuff of convenience is always nice, right? So let's show one final thing about this, which ties into that. Sometimes instead of just creating the table, you want to actually, well, store it. So in that model, if you add file is and then some kind of file name, it automatically saves the file on that location. And then this is a nice function to know. It works for any kind of URL. It just means open a URL with my favorite browser, my default browser. So this is a nice way of saying quickly create this model, save the file, and then open the HTML in my browser so that you can easily copy paste it to your work file. Now, of course, whenever you're using regression models, one of the important, well, not just regression models, whenever you do any kind of statistical analysis, it's critical that you look a bit into the model diagnostics. So how well does a model here actually work? Of course, we're not going to discuss in detail how to do proper model diagnostics. This is something that you really need to learn in a proper statistics course, but we're just going to show you how to do this in R. Oh, and by the way, we're talking about comparing and diagnosing models. So the first part is really just, if you have two models, how can you determine whether one model is better than the other? Let me just clean this up. So say you fit two models, then you often want to say, well, is this model a significant improvement over the previous model? And this is actually what we use the Anova function for in R. So previously I mentioned that we have the AOV function for doing what we often call the Anova statistical test. Here we have the Anova function for the analysis of variance for these different models. And this just tells you whether one model is a significant improvement over the other, which in this case is the case. Just. So it shows us that adding the interaction effect is actually a good thing to do. It's a better model in that sense. We'll discuss this a bit more in more detail in the more advanced statistical part, where we focus on generalized linear models, where this is particularly important. Now, for the diagnostics, the main thing is just that you want to have some general information about how to interpret, well, whether the model fits correctly, so to say. And typically you have some plots that you can use for this. And here we have a little bit of messy looking code, but I'll discuss it step by step. Actually, the code that we're going to discuss is just this one, plot M. And before I mentioned that one of the nice things about assigning a model to a name is that this allows you to do several different things with it. So we can ask for the ANOVA of model 1 and 2 to compare them. We can ask for the summary of a model to look into what it actually tells us. We can also plot a model, and then there's also some default behavior that R has whenever you perform this. Now, whenever you plot a model in R, what it does is it automatically gives you 4 different plots for diagnostics. But it's a bit weird, right? Because if you plot 4 different things, you can't just make one single plot out of it. So what happens is that you see here, I used plot M, and then it asks me, hit return to see next plot. And that is really what happens. If you now stand on this line and hit enter, it moves to the next plot. And that is useful, but it's also slightly inconvenient and also not very R-like to have like this sudden interaction that you need to have by pressing enter. It also makes it impossible to include this stuff in an R Markdown file, for instance. So that's why a nice thing to discuss here is what you can do if you have multiple plots to put them still on one single, well, in one single window, so to say. So here we have the par mfro is 2, 2. What we're saying here is we're going to specify some parameters, and specifically we're going to say that the plotting device should be split into 2 rows and 2 columns. So what this means is that where we first had one device for plotting, we're now splitting it into basically a grid of 2 by 2. And if we do this and then ask it to plot, well, it automatically considers you want to plot 4 things. So I'll just plot them in this grid. So this then is a nice way to quickly generate these 4 different diagnostics plots. And again, we're not going to discuss how to interpret them. I've put a link here which discusses nicely, also specifically for these plots, how to use them for proper regression model diagnostics if you want to look into them. Then one final note here. If you've done this, you said, well, I'm going to plot now in a 2 by 2 grid. It's often a good plan to afterwards also undo this, to say that in the next thing that we're going to plot, I just want to have, again, a plot window with 1 row and 1 column. Because otherwise, whenever you plot something, and this is just a silly plot, it would still always make up these 4 plots and then start over again. So here we reset it so that we again go back to our basic default plotting mechanics. So now we're almost done. Technically we are already done. I just want to show you one nice additional thing. But actually I'm still a bit on the fence of how nice this is, but it's good to learn about. So in R you also have this thing called Jmovie, which is a package which basically has some kind of GUI, so a graphical user interface, to run something that is similar to SPSS in the sense that you just get a data frame and you can click stuff instead of using syntax. But then it does everything on top of R, and you can also, where you can normally in SPSS paste everything to SPSS syntax, you can now paste it to R syntax. So this can be a nice gateway drug if you're used to SPSS and you want to get into R, but you find the leap a bit too far, then this might be a nice way to ease yourself into it. But also, aside from using the GUI, you can use the package directly in R by installing the Jmovie package. And then one of the nice things about that is that you can basically do statistical analysis in R, but it's the output is basically identical to how you would see the output in SPSS. So if you're very used to interpreting Anova tables in SPSS or regression tables in SPSS, this might be a nice way to ease yourself into R. And the reason I'm on the fence about this is that I would say just invest the time and learn how to do it in R properly. Because, I mean, it's just more convenient. It makes more sense. You shouldn't learn statistics stuck to a certain kind of package that you know how to do it, but only in SPSS. But again, it can be something which can help if you are struggling with learning how to do stuff. So here we basically say, we're going to do an ANOVA of the capital data. The dependent variable is private, the factors is country, and the post hoc is also done on country. And what you then get is output as you would know it from SPSS format. Now you would first have just the ANOVA results telling us, yes, there is a statistical difference between these groups. And then the post hoc test where you have all these comparisons between the countries with the typical scores that would be reported by SPSS. And the same thing if you do a t-test, in this case independent samples, IS test. If you want this one, then again the output is just very similar to how it would be reported by SPSS. It actually tells us that it wants to plot something. So sometimes whenever it says invalid graphic state, this is a nice opportunity to discuss this, then there's something wrong with your plotting window. And it might be that we've broken it to something like this. Whenever you encounter this, just do def off, which says shut off my plotting device. And then it resets it. Right, so by default it also gives you a simple plot for how to see this difference in the independent samples t-test. So again, it's not necessary to do this. You don't need Jmovie, but if you're very used to SPSS and have a hard time getting into R, but do want to make the step, but especially the statistics part is something you're just very used to the other formats, this might be a nice way to ease yourself into it. And that's all of it. So basically this tutorial introduced t-test, ANOVA, and linear models in R, a bit about diagnosing and a bit about using Jmovie. In the next video, we're going to discuss a bit more about how to move from this statistical modeling in R to some more advanced statistical modeling. And that's actually pretty cool because you'll see that if you go from linear models to more advanced models, such as generalized linear models or multi-level models, that the syntax stays very much the same. And also things like the Ggplot package all still work. So you have the kind of similar workflow that you'll be using for really these more advanced statistical methods.